Hello, in this video we will be looking at the coin change problem and we will also compute the time complexity and space complexity of the solution that we will be building here, and the solution will be built in JavaScript. Before jumping into the solution aspect of it, let's first understand what this coin change problem is. Let's say we are given a set of coins with us. What we need to do is we need to reach a certain amount from this coins, and to reach this amount we need to use the minimum set of coins possible to reach that amount. In terms of input, let's consider this first example wherein we are getting coins with denominations 1, 2 and 5. What this will mean is that we will get one denomination, let's say 5 cents, we will get another denomination, let's say 2 cents, and we will get another denomination, let's say 1 cent. So we have this three denominations with us, and from this three denominations, each denomination I can use as many of times I want. What I mean by that is I can use this 5 2 times or 3 times or 4 times, as many times as the solution requires me to use. But the thing is, I have to use n number of times only from this three denominations that I have. I cannot use any other denomination to reach whatever amount I want to reach. So let's say in this example we wanted to reach the amount of 11 cents. So what we can do is we can use this 5 cent coin 2 times. So this gives me 10 cents, and then I can either use 2. 10 plus 2 is going to give me 12 cents, which is not what I'm looking for. I'm looking only to reach an amount of 11 cents. So in that case, what I will do is I will use these two coins and I will use this 1 cent coin to give me my amount which I was looking for, which was 11 cents. So this is the crux of the problem statement, and because I was using 3 coins, I said the output is 3 because this was the minimum number of coins which I used to reach my solution. Another use case that can be is that let's say you receive an input of just denomination 2 cents, and we are saying that we need to reach an amount of 3. In this case, if I just have this denomination, I cannot really reach the amount of 3 because if I just use 1 coin, it's 2 cents. If I use 2 coins, it's 4 cents. So it's going to never match the amount that I'm expecting, which is 3 cents. In that case, the problem statement says just return -1. And that's the two use cases which we are going to be dealing with. And let's try to build a solution on top of this problem statement now. In this problem statement, we are told to find the minimum number of coins that will be required to reach our amount. And whenever there are this kind of problems wherein we are asked to find either the minimum something or the maximum something, in those cases sometimes DP solutions give us the optimal results. Now what we are going to say when we say we are going to use dynamic programming is that with dynamic programming comes its own components. So to solve any problem via dynamic programming, we have to use a base condition. From that base condition, we will try to form a equation which we will be repeating to reach a final solution. So we will be dividing the problem into smaller sub problems, and we will accumulate the results of all these sub problems to reach a final solution. Now to start with the base case, that is usually the tricky part. What do we use as a base case if I want to apply dynamic programming? Now in this case, for base case, it is something that can be a smallest problem that we need to solve. Now what if we say that our smallest problem is 0? I want to reach an amount of 0. In that case, how many coins will I be needing? If I need to reach an amount of 0, I need to use 0 coins. And this 0 which I am getting as my solution, I will use this as my trigger condition. And I will also maintain a DP array. Why DP array? Because usually in dynamic programming solutions, whatever state we receive of these smaller problems that we divide our main problem into, all these smaller problems, the solutions of them we stored in this DP solutions array, and we will keeping on putting the solutions in the array as we iterate through our subproblems, and then based on this DP array we will accumulate all the solutions from our smaller subproblems and reach a main solution that we are looking for. Now in this case, I said that the base condition, which is my smallest subproblem, is that I want to reach an amount of 0. That's what I mentioned. In that case, my trigger condition will be that in this DP array, I will initialize for amount of 0. So the solution array wherein the amount is 0, my solution is 0. So in this array, whatever values go, each index is going to be my amount index which I'm going to track. And in the end, what I'm going to do is, my aim here is I need to reach this amount which I'm given. So my solution is either going to be DP of amount, or if I am not able to reach a solution, I will return -1. So either this DP of amount, or I will return my final solution that I got iterating through this subproblems and building my DP array as I go through this smaller subproblem solution. Now that we have decided our base condition, what we need to do is, from this base condition, try to solve more smaller subproblems, and from this expression that I mentioned earlier, which we will be repeating because this is a dynamic programming approach, we will keep on repeating this expression to solve our subproblems and then reach a grand solution. Now to form this expression, let's take an approach something like this. Let's say we have this matrix, and on this side of the matrix we have denominations 1, 2 and 3, and on this side we have the amount we want to reach. So we started with a smaller subproblem which was 0. Now let's expand the scope of the problem a bit by first including amount 1, amount 2, amount 3 and so on. But for the sake of explanation, let's just first consider that we increased the scope a bit from 0 up to 3 now. And what we will do here is basically find the number of coins that we need to reach a solution here, which is amount of 1. Now I know that to reach amount of 1, I just need 1 coin of 1. If I try to use denomination of 2, I cannot really reach this amount because the amount itself is less than the coin value which we have. So if the amount is less than the coin value, we cannot really use the coin, which translates into something like this: amount minus coin. If it is greater than equal to 0, only then you can use the coin, otherwise you cannot use the coin. So we said amount is 1, the coin is 2 here, which is -1, so you cannot use that coin. And similarly, the amount is 1, the coin is of denomination 3, which is -2, which cannot be used as well. So it has to follow this pattern wherein amount minus coin will always be greater than equal to 0 to be able to use the coin itself. And this one I can represent into something like this. So I said amount minus coin. What was the amount? Amount was 1 and the coin was also 1. So this 1 minus 1 gave me 0. So I will put this representation into this, wherein this will be f of 0 that I have. Similarly, let's go to this amount of 2 to try to find the number of coins that are required. For the amount of 2, which is substituted here as 2 minus what is the coin that we are looking for. The coin that we are looking for is coin 1. So we will say 2 minus 1 is going to give me 1. And this is going to be used 2 times to reach my solution. So I will say here that I need 2 coins of 1 to reach my solution. So final solution is going to be 2 here. And similarly, if I just go a step back, wherein in my previous one I represented this as f of 0, I did amount minus coin, which gave me 0, and this needed me to add 1 coin to reach my solution of 1. So I needed to do addition of 1 to reach this 1 which I was looking for. So I said I did plus 1 to reach my solution. Now here I said 2 minus 1 gives me 1, and I need 2 coins of this 1 to reach my solution. 1 is missing something to reach this 2, so I'll just say plus 1 like I did here. So I said 1 plus 1 gives me this 2, and this is represented by 2 minus 1, which is the 1 that I got. So I will say here f of 1 here. Now moving forward, I say to reach the amount of 2, how many coins of 2 do I need? Similarly, I will say amount minus coin. Amount is 2, coin is 2, gives me 0, and I know that I need to use 1 coin of 2 to reach solution amount of 2. So 0 plus something is going to give me this one. So this is 1. Now I see we are starting to form this pattern here, which exists saying amount minus coin plus 1 gives me the number of coins that I am looking for. And this I will represent something like f of 0 here, because amount minus coin gave us 0. And if I try to say I need to reach amount of 2 with the coin of 3, it is not possible because amount minus coin, so 2 minus 3 is minus 1, minus 1 is not greater than or equal to 0, so I cannot reach a solution here. Similarly for 3 now, so let's first just see what we are trying to do here. We first considered for dp of 0 here. When we considered, we said that hey, let's break down our smallest sub problem. And what was our smallest sub problem that we looked at? It was this dp of 0. So to reach amount of 0, we needed 0 coins. Then we expanded our scope a bit from 0 to 1, and we said, hey, to reach this amount of 1, how many coins of 1 do I need? How many coins of 2 do I need? How many coins of 3 do I need? So I just said, let's explore by expanding the scope of a smaller subproblem to 1 now. Then we said, let's expand the scope to amount of 2. So then the scope of the subproblem expanded further. And we're just repeating this expansion now by moving forward to 3. And we will try to form a pattern from this. And then the expansion is just going to repeat itself based on the expression that we are forming here. And what we will do now is, for 3, to reach this amount of 3, how many coins of 1 do I need? I will say amount is 3, coin is 1, that is giving me 2, plus something is going to give me the number of coins. Now we have been keeping on adding 1 in the past. So we added 1 here, we added 1 here, we also added 1 here to whatever amount minus coin output had come. Similarly, what we will do is we will say plus 1 now. Now this is the critical aspect wherein we define our expression. So this is to validate the expression that we are trying to form. and then we will just use this solution expression to use in a development part of it. So what we said, 3 minus 1, 2, which was here, plus 1 give us 3. So here it says 3 minus 1, 2. I will represent this as f of 2, and it needed me to use 3 coins of 1 to reach my solution. All good. Moving forward to the coin of 2. So how many coins of 2 do I need to reach my solution? Similarly, what we will do now is say that what is our amount that we want to reach. The amount we want to reach is 3. What is the coin? 2. 3 minus 2 is giving us 1. So this is going to be f of 1. This plus something is going to give us a solution. So 1 plus 1 is 2. And what we are saying here is that 3 minus 2, 1 plus 1 gives us 2. So this is 2. So I need to use 2 coins to reach my solution. Now, what critical aspect this has is that when I say add 1 here, this doesn't mean that I'm going to use the same coin twice. This just says we are going to use 2 coins. This just says we are going to use 3 coins. This just says we are going to use 1 coin. This just says we are going to use 2 coins. And this just says we are going to use 1 coin. But this coins can actually vary. So here in this case, what we did was we said 3 minus 2 gives us 1. We said that here we are getting 2. So what this means is from 2 we are going to use 1 coin and then 1 coin extra. So this plus 1 that we keep doing is 1 extra coin from whatever coins you were able to form with this equation. So it says that 1 minus 1, which is 0, plus 1 extra coin, which was the coin of 1 itself. 2 minus 1 gives us 1. Along with this, it says give me 1 extra coin, and similarly for rest of them as well. And here now we said use 1 extra coin and give us a solution. So 1 coin of 2 and 1 coin of 1. 2 plus 1 is 3. Now what we will do is move forward to this block. So this block is 3 minus 3, which is gives us 0. 0 plus 1 is going to give us 3. So now what we get here is f of 0, because this itself is 0, and this is going to be 3. So we said that for reaching a solution amount of 3, we need 1 coin of 3, 0 plus 1. And we have filled this matrix following this iterative pattern which we were following. Now let's jump on to the next aspect of it. From all these solutions, what solution did we really want to pick? So we said that for this 3, we found one way wherein we could use 3 coins, another way wherein we could use 2 coins, and another way wherein we could use 1 coin. From these 3 that we found, the minimum was 1 coin which we were using. Hence the solution is going to be minimum of whatever possibilities that we have, and whatever possibilities that we have depends on the number of coins that we have, and the number of coins depends on the input that we receive. And here we are doing plus 1 to amount minus coin. So finally we are saying amount minus coin. Whatever solution you get for this one, you just do plus 1 to it. So that's the expression that we were looking for. Similarly, just to reiterate how this feeds into this is amount was 1, coin was 1, you got 0, you needed 1 extra coin plus 1 to reach a solution. And using this as a base now, let's form a solution in JavaScript, and then we will move on to the time complexity and space complexity aspect of it. Code aspect of it, we first said we will put a base condition, we will be using a DP array, and then we will be using this expression that we have formed, which says that amount minus coin plus 1 to keep on repeating our smaller subproblem solutions to reach a final solution. And I will go through all of them step by step. And let's say we have a DP array here. So I will say use a array of amount plus something plus amount and fill it with amount plus 1. Now, why do I fill it with amount plus 1 and why do I need an array of amount plus 1? This amount plus 1 is a impossible condition that we are handling. What we need to do is, the goal here is we need to find a solution to reach a specific amount, and if we cannot form that amount, we have to return minus 1. And if I just say fill this with 0 and then I try to keep on computing the values, this will not work because it will take the solution of my input array that we have here from DP array, and this will make the result invalid, because what we need to do is we are not going to consider this 0, we are just going to use a base case and we are going to keep on building a solution that we are looking for. So we just fill this with some impossible value, and in this case what happens is that amount plus 1 is an impossible value. So we want to make sure that whatever final output we will be returning is going to be either valid or it's going to be minus 1. And then we will just put a check here saying, hey, in the end, after we are done everything, if this is still filled with amount plus 1, which is our impossible case, then you have not yet reached your solution and you will not reach it. So you just return minus 1. So what I mean to that is something like this. So DP of amount is not equal to amount plus 1, which is our impossible case which I mentioned. In that case, you just return DP of amount, which is going to be our final solution, or you have not reached a solution and you return minus 1. So you use this DP array to solve your smaller subproblems, and in the end, this is going to be the output that you're going to return, and if you don't have it, you just return minus 1. And what we said is we will be having a base case. Base case meant that DP of 0 is going to be 0, which just translates to saying that, hey, if you have input of 0 amount that you have to reach, what are the number of coins that you're going to need? You're going to need 0 coins. And this is a base case. After this, what we're going to do is use a loop from a equal to 1, because we already found solution for 0th case. We don't need to repeat it again, and I will keep on going until I reach my amount. I will keep iterating to reach my final amount that I'm looking for, and then what I will do is I will try to form this smaller amount. So I will say, hey, I want to form amount of 1, then I will try to form amount of 2. So I will have this smaller subproblems that we just now covered, saying first the smallest subproblem is 0 amount you want to reach, then you want to reach amount of 1, then you want to reach amount of 2, then you want to reach amount of 3, so on until this amount that you want to ultimately reach. That's why we said a is less than or equal to amount. Now we need to try to use the coins that we have to form the amount, whether it is possible or not. So I will say C of coins, whatever coins I have received as my input in this function, if amount minus coin, now the current amount is not the final amount, it's just this A. So this B translates to A, and the coin is C here. So if A minus C is greater than equal to 0, that means you can use the coin because the denomination itself is not higher than the amount that you want to use in single usage. In that case, what I will say is dp of A, that is the amount I want to reach, is going to be, first let's just form the equation and then let's change it. The equation that we wrote earlier was that we will find amount minus coin, which was amount minus coin representation as A minus C, and then we added 1 to it. This is what the core expression that we formulated. Now, because this is a loop, we will just tweak it a bit. And we said that when we found the solution for amount of 3, we found it for using denomination 1, we found it for denomination 2, we found it for denomination 3. And from this 3 denomination, we picked the minimum one. That's the tweak that I mentioned. So we want to use something minimum from the solutions that you already have. So what I will say is met.minimum from the solution that you already have from the previous coin, because these coins go in iteration. So you will go from, if you have like denominations 1, 2 and 3, it will use denomination 1 and form a solution. It will use denomination 2, form a solution. Similarly use 3 and form a solution. So I need to use the minimum from an already existing solution and my new solution, which is going to be dp of A minus C that we have. And from this two, I will use the minimum solution and just fill this here until I reach my amount. And then in the end, if my amount has been properly formulated, which is not amounting to amount plus 1 now, that means you have been able to form the solution that you were looking for, in the sense that this basically translates to amount minus coin plus 1 extra coin that you wanted to use. That 1 extra coin can be this coin itself, or in a complex case that we saw with the coins of 2, when you wanted to reach an output of 3, you had to use coin of 2 and coin of 1, which was the 1 extra coin from 1 that we wanted to use. So this is plus 1 extra coin, and that's pretty much it. This is the core logic that we basically have to deal with here. And then you just use like the previous solution, A minus C, just to plus 1 to it. And that's how we reach a solution. Now, in terms of time complexity and space complexity, what we will say here is the time complexity is formed by something. Now this time complexity is formed by this outer loop. Along with this outer loop, we are going to go in another loop here for the coins that we have. And this outer loop is based on the amount that we receive here. So this amount, let's represent it by A. And then what we said was, along with this outer loop, we run an inner loop with this denominations that we receive. And we can represent this denominations as C. So it will be big O of A into C, which is this outer loop forming the big O of A time complexity. And then for each amount iteration that you cover, you're going through the coins that you have. So it is A into C. And in terms of space complexity, what we will say is it is big O of A, because we're just going to create an array here with the dp having amount plus 1 filled into it, and this is just going to be amount plus 1. So this is big O of A plus 1, which is basically translating into big O of A to reach the solution. And that's pretty much it. Thank you for watching. Please like and subscribe.